Welcome to the Deep Dive, where we cut through the noise to bring you the most compelling insights from cutting-edge research. Today, we're plunging into a topic that underpins nearly every digital interaction you have: error correction. Every time you stream a movie, send a text, or get a crystal clear signal from a satellite thousands of miles away, there's an invisible magic making sure your data arrives perfectly, even through interference. But that invisible magic often comes with a hidden cost, a massive computational overhead that has historically limited how far we can push our digital systems.
Indeed. It's a fundamental bottleneck, really. Today, our mission is to unpack a truly groundbreaking paper titled Margin Propagation-Based XOR SAT Solvers for Decoding of LDPC Codes, penned by Ankita Nandi, Shantanu Chakrabarti, and Chetan Singh Thakur. They've found a clever shortcut, a radical new approach to make this critical data protection dramatically more efficient without sacrificing an ounce of performance. This work genuinely redefines the trade-offs we thought were immutable in balancing power, area, and speed for critical communication systems. It's quite exciting stuff.
Think of it as finding a secret, hyper-efficient pathway through a dense, computationally heavy forest. They're getting us to our data destination faster, with significantly less effort and energy. We'll be looking at how they've combined some really interesting mathematical concepts with hardware-aware design principles to achieve this, ultimately leading to more robust, faster, and incredibly efficient digital communication for all of us, from our smartphones to deep space probes. So before we dive into this paper's ingenious solution, let's set the stage a bit. Our listeners are probably familiar with the general idea of error correction, but what exactly are low-density parity check, or LDPC codes, and why are they considered such a cornerstone, almost the gold standard, of modern digital communication today?
Right. LDPC codes are, well, without exaggeration, fundamental to our digital infrastructure. They're absolutely essential for reliably transmitting information over noisy channels. And let's be clear, almost every channel you use today is inherently noisy. It's just the nature of physics. Whether it's the radio waves for your Wi-Fi, the complex signals of 5G networks, those intricate satellite links that power your GPS or bring you weather forecasts, or even how data is safely stored on the solid-state drives in your computer, LDPC codes are working silently in the background. Without them, honestly, your video calls would be a constant stream of pixelation, data transfers would be plagued by corrupted files, and the reliability we now simply take for granted, it would just vanish. Now, these codes were actually first introduced by Robert Gallagher way back in 1962.
Wow, 62, that's surprisingly early.
It was. They were really ahead of their time. They only gained widespread popularity much later, sort of in the early 2000s. And that was thanks to advancements in computational power that could finally handle their decoding complexity. Their rise was also driven by their near-optimal performance. I mean, they achieve error correction rates incredibly close to the theoretical limits defined by Claude Shannon's channel capacity theorem. It's remarkable, really, the low density part of their name. That refers to the sparse connections in their underlying graph structure, which is a key design element. This sparsity is crucial because it means that each check equation only involves a few bits, and each bit participates in only a few check equations. This structural simplicity, despite the overall complexity of the code, is what makes them manageable for very long, powerful codes. It enables efficient encoding and iterative decoding. And that's why they're now adopted in standards like DVB-S2 for satellite TV, Wi-Fi 802.11 NAC, and 5G. They're everywhere.
So they're not just any error correction. They're an incredibly powerful, near-perfect digital spell checker that works tirelessly in the background, ensuring our data integrity even under the most challenging conditions. It's like having an invisible, ultra-resilient guardian for every byte of information we send or receive. Okay, now the paper highlights a fundamental challenge inherent in these powerful codes: decoding them to fix errors. What's the core problem here that makes it such a persistent dilemma for engineers, pushing them to constantly seek new solutions?
Right. The core problem is, well, it's profoundly difficult. At its heart, finding the optimal way to decode an LDPC code, what we technically call minimum distance decoding or maximum likelihood ML decoding, is known to be an NP-hard problem. Now, for those unfamiliar, NP-hard isn't just a fancy term. It implies something very specific and very challenging for computation. It means that as the complexity or length of the code grows, the computational resources required to find the absolute best, most perfect solution don't just increase linearly, they grow exponentially.
Okay, let's unpack that intimidating NP-hard label a bit more. You're saying it's like trying to solve a Rubik's Cube with a million sides, where every twist and turn could lead to a quadrillion new states. It's theoretically possible, but practically impossible to find the optimal solution in a reasonable time frame for a real-world scenario. And for LDPC, that reasonable time frame isn't a few hours, it's often milliseconds, right?
Exactly. You've nailed it. The complexity isn't just in finding any solution, but in the sheer number of possible states or combinations you'd have to explore to find the one correct sequence of moves, or, in our case, the one correct transmitted code word. And for LDPC decoding, that one correct sequence changes every millisecond based on new incoming noisy data, making a brute force approach absolutely impossible. For practical applications where speed and efficiency are paramount, like your phone decoding a 5G data packet, such an exponential increase in computation simply isn't feasible. You literally cannot wait days for a single packet to decode. So, in practice, because optimal decoding is intractable, we have to resort to approximate methods. These generally fall into two main families. First, there are belief propagation, BP, algorithms. This includes methods like the sum product algorithm, or SPA, and minsum. These algorithms offer superior decoding performance, often getting remarkably close to that theoretical optimum we discussed. However, they come at a higher computational cost because they often involve complex floating point multiplications, divisions, and sometimes exponential operations. These are really resource intensive for hardware. They consume significant power, chip area, and take more time to execute. The second family is bit flipping BF algorithms. These are generally much simpler and have a significantly lower computational complexity. They operate on binary decisions and often use simpler logic. The trade-off, though, is that their decoding performance typically lags behind the belief propagation methods. They don't quite achieve the same level of error correction, meaning they might miss some errors or converge less reliably, especially in very noisy conditions.
So it's always been this inherent tug of war, hasn't it? A constant compromise. Do you want the absolute best possible error correction, which costs a lot in terms of power and speed, or do you opt for something faster and cheaper, knowing you're sacrificing some performance? Until now, we've always had to accept some degree of this trade-off for practicality. It seems unavoidable. Okay, here's where it gets really interesting, because this paper takes a different angle to try and break that compromise. If these traditional approaches face an inherent tug-of-war between performance and complexity, how does this paper find its secret pathway? It starts by reframing the very problem itself, treating LDPC decoding as a special case of XORS problems. What exactly is an XORS problem, and what conceptual leap does framing LDPC decoding this way involve?
That's a great question because this reframing is a crucial initial step. An XOR problem is fundamentally about finding an assignment of Boolean variables. Think of them as simple zeros or ones that satisfies a set of XOR clauses or parity check constraints. Imagine you have a set of logical equations where each variable can only be either 0 or 1, and you need to find specific values for those variables that make all the equations true simultaneously. The XOR operation, as you know, returns true only if an odd number of inputs are true. So an XOR clause basically states that the XOR sum of a specific subset of variables must equal 0 or 1, depending on the constraint. It's a logic puzzle. The paper gives a great simple example in Figure 1a to illustrate this with a 3-variable XOR set. You have 3 variables, U1, U2, U3, and 2 parity check constraints, C1 and C2. Constraint C1 might say U1 XOR U2 equals 0. C2 might say U2 XOR U3 equals 0. The goal is to find values for U1, U2, U3 that satisfy both C1 and C2. In this specific case, the valid code words, the solutions that satisfy all constraints, are 1000 and 111. These are the only combinations of zeros and ones for U1, U2, U3 that satisfy both equations.
Okay, so an XOR set over just finds any solution that fits the rules in a valid combination. But with LDPC decoding, we're not just looking for any valid code word, are we? We've received something noisy, maybe corrupted, so we need something much more specific. That leads to a critical distinction, I imagine.
Precisely. That's the crucial nuance and the challenge this paper addresses head-on. For LDPC decoding, you receive a noisy version of the transmitted data. This received signal is often not a perfect 0 or 1 for each bit. It might even be a real valued signal indicating a probability of 0 or 1. So the decoding problem becomes, find the nearest valid code word to that received noisy input, not just any valid one. The paper illustrates this beautifully in Figure 1b and 1c. You can visualize all possible assignments of zeros and ones as nodes on a discrete lattice, like points on a multidimensional grid. The valid code words are specific nodes on this lattice. When you receive a noisy signal, it might not directly correspond to a valid code word. It might even be real valued, existing within the volume of the lattice, sort of. Not quite a node, but somewhere between them. The search for the nearest valid code word can then be seen as an optimization problem. In this view, valid code words are the maxima of an objective function. Think of it like trying to find the highest peaks in a complex mountain range, where each peak represents a valid code word. You start somewhere on the slope corresponding to your noisy received signal, and you need to climb to the nearest peak. The challenge is that this optimization landscape can be highly non-convex. This means it's not a smooth, simple ascent to one clear peak. It's full of many local maxima, false peaks, or smaller hills that can trap an algorithm before it finds the true closest code word, which would be the global maximum in your vicinity. It's easy to get stuck on a smaller hill instead of finding the highest peak closest to where you started. This intricate navigation is precisely why optimal LDPC decoding is so difficult. You're trying to find the most likely original message by efficiently traversing this complex landscape.
So given this complex mountainous landscape of possible solutions with all these false peaks, how do decoders typically navigate it when they're using an optimization approach, trying to climb to one of those elusive peaks?
Well, many bit-flipping algorithms, especially those that try to leverage soft information, fall under the umbrella of gradient descent bit flipping, or GDBF algorithms. These approaches use the gradient of an optimization function to guide an iterative process. Imagine you're blindfolded on that mountain. The gradient tells you which way is steepest up from your current position. So at each step, the algorithm essentially walks across the optimization landscape, trying to climb towards a maximum by flipping bits, changing zeros to ones, or vice versa, in the direction that seems to improve the objective function the most. It's like feeling your way uphill. Now, early GDBF algorithms often relied on hard decisions. They only cared if a bit was a binary 0 or 1. Very basic. But modern communication channels are much richer. They provide soft information. This means you get not just if a bit is likely a 0 or 1, but how confident that assessment is. For instance, a signal might be very likely a 0 with high certainty, or only slightly more likely a 1 than a 0 with low certainty. Historically, very few GDBF algorithms effectively exploited this richer, soft information, meaning they weren't making the most of the valuable data available to them. They were kind of leaving performance on the table.
It sounds like a powerful idea in principle, using the gradient to guide the search, but yeah, with clear limitations if it's not fully leveraging all the available soft information. The paper mentions that most earlier GDBF works have a similar form of objective function. What's the significance of that? Does it imply a certain stagnation in the field until now?
That's a critical observation. It absolutely suggests a lack of fundamental innovation in the underlying mathematical approach to the objective function itself. For decades, researchers explored variations and tweaks to parameters within a broadly similar mathematical structure for these GDBF algorithms. And while these incremental improvements were valuable, they didn't fundamentally alter the computational cost or convergence characteristics in a truly significant way. This paper, however, explicitly states that they propose an objective function that is not equivalent to these existing ones. This is a crucial distinction because it opens up an entirely new way of navigating that complex optimization landscape, rather than just optimizing within existing paradigms. It's not just a tweak, it's like they found a different blueprint for the mountain range, allowing for a potentially much more efficient path to the peaks.
Okay, so they're starting from a new mathematical foundation. Interesting. This brings us to a key ingredient in their novel solution, margin propagation. What exactly is margin propagation, or MP, and why is it such a game changer for hardware implementation and overall efficiency? Especially when we're talking about those resource-intensive multipliers you mentioned.
Right, margin propagation, or MP. It's a principle that was first introduced to approximate different log-sum exponential functions using only piecewise linear functions. Let's break that down a bit. Log-sum exponential functions, they pop up a lot in probability calculations, especially when you're combining many uncertain inputs or dealing with soft information, like in decoding. They naturally handle operations like maximum likelihood decisions, but they tend to be computationally heavy because of the exponentials involved, which are very expensive for digital circuits. MP's genius is in finding a simple series of straight-line segments, a piecewise linear approximation that gets you almost the same answer as the complex curve, but without all that complex, energy-hungry math. Think of it as simplifying a curve into connected straight lines. The truly groundbreaking part, and why it's such a game changer for hardware, is that the resulting circuits and systems obviated the use of multipliers. This is paramount for computational and hardware complexity. Multiplications are inherently complex operations for digital circuits. They consume significant power, often much more than addition. They require a substantial amount of silicon area on a chip, which directly impacts cost and size. And they take more time to execute compared to simpler operations like additions or comparisons. So replacing these complex multiplications with just simpler operations like additions and comparisons, it dramatically reduces these demands and makes the hardware much more compact, energy efficient, and faster. This isn't just a technical tweak, it's a paradigm shift, allowing for what this paper calls an order of magnitude reduction in the hardware footprint. It makes advanced error correction feasible for devices we could only dream of fitting it into before.
Wow, so if you can completely avoid multipliers, you're essentially making the underlying hardware much, much simpler, faster, and dramatically more energy efficient. That really is a huge aha moment for anyone thinking about designing compact, low-power devices, right? From tiny sensors to battery-powered wearables, because every watt and every nanosecond counts. It fundamentally changes the design equation.
Absolutely. And this isn't just a theoretical concept or a brand new idea that hasn't been tested. This principle has already proven its value in various real-world applications. It's been successfully used in everything from analog classifiers, which can categorize data efficiently at the edge of a network, to digital accelerators for machine learning tasks, and even in field programmable machine learning processors. For instance, in analog classifiers, MP allows for extremely low power and fast decision making, which is crucial for battery-powered IoT devices. In digital accelerators, it simplifies the complex mathematical operations involved in neural networks, speeding up inference and reducing the power footprint. So there's strong demonstrated track record for margin propagation, making complex computations more feasible in power and area constrained environments. It works.
Okay, so we have this new way of framing the problem XOR-SAT and this incredibly efficient mathematical approximation technique, margin propagation. What happens when you combine these powerful ideas into the MP-XOR solver for LDPC decoding? What's the big picture of this new approach, and how does it practically translate into a working decoder?
Well, when you combine these elements, the proposed MP-XRS solver emerges as a novel, low-complexity LDPC decoder. And the key thing is, it achieves results strikingly close to the benchmark sum product algorithm, or SPA, but with significantly reduced computational demands. It's effectively giving you SPA-like performance without the SPA-like cost, which is huge. The approach, as outlined in Figure 2 of the paper, involves several innovative and carefully designed steps. First, they design a custom objective function specifically for exavisar problems. They use what they call a log-sum exponential function, log QH. Now, this isn't just an arbitrary mathematical choice, it's designed from the ground up to inherently simplify the calculations. When its gradient is taken, which is the core of how GDBF algorithms climb the mountain, remember, this function is engineered to primarily rely on simpler operations like additions and comparisons rather than complex multiplications. This mathematical choice immediately helps eliminate multiplications from the core objective function, making it hardware-friendly from its very foundation. The second step is tailoring this function specifically for LDPC decoding. They modify hog QH to create HLDPCQRDH by adding what they call an extrinsic factor. This factor is absolutely vital because it's what biases the solver to find the closest valid code word to the noisy received signal, not just any valid code word. Remember, for LDPC, we care about finding the solution nearest to what we actually received, not just any solution that satisfies the parity checks. This extrinsic factor brings in that crucial channel information. Finally, in the third step, they derive the gradient of this HLDPC function. And here's where margin propagation comes in to seal the deal on efficiency. They replace the complex probability scores within this gradient calculation with simpler margin propagation-based probability scores. These ME scores, as we discussed, are designed to not require multiplications, instead relying on additions and comparisons. They also incorporate additional heuristics, sort of smart, practical rules of thumb based on observation, to further refine the bit flipping process, guiding the decoder more effectively towards the optimal solution.
So it's a meticulously engineered three-stage process that systematically eliminates computational bottlenecks. Okay, what does this all mean for us? What are the key contributions that make this MP-XOR-SAT framework so significant in the broader landscape of error correction? It sounds like more than just an incremental improvement. It sounds well, quite radical.
You're absolutely right. It's a substantial advancement. Let me integrate the key contributions into a narrative that truly highlights their impact. The foundation of this entire framework, which they call MP-XOR-SA, is its brilliant use of margin propagation. By employing this piecewise linear approximation, they've effectively re-architected how XOR-S solvers are implemented at a fundamental mathematical level. This leads directly to their second and arguably most monumental contribution for hardware designers. The resulting MP-XOR-SAT decoders do not require multiplications. This is a truly game-changing characteristic, as it leads to a dramatically lower computational and hardware implementation complexity compared to even the sum product algorithm. SPA, while highly performant, is notorious for its multiplication-heavy operations. Imagine designing a chip without having to allocate significant area, power, and clock cycles to complex multiplication units. This drastically reduces the cost, size, and energy consumption of the decoder. It's a huge win for hardware folks. And this efficiency doesn't come at the expense of performance. That's their third major breakthrough. When used for LDPC decoding, this MPX or SAT solver takes an astonishing 10 times fewer code iterations to achieve its performance compared to many state-of-the-art gradient descent bit flipping algorithms. That's huge. What's even more impressive is that it takes the same number of code iterations as the sum product algorithm, which is the benchmark for performance, and achieves error rates that are within at least 0.1 dB of SPA. To put that into perspective, zero point 0.1 dB is such a small difference that it's often considered almost indistinguishable performance-wise in many practical scenarios. Yet it's achieved with a fraction of the computational effort of other GDBF methods and in the same number of steps as SPA. And finally, bringing it all together, the proposed MP-based XOR-S algorithm possesses lower overall computational and hardware complexity than the sum product algorithm itself, even while matching its iteration count for comparable performance. This is really the holy grail for engineers. High performance with significantly reduced computational and hardware overhead. It truly revolutionizes the trade-off landscape we've been stuck with for so long.
That's an incredible set of advancements. Just staggering, really. You mentioned earlier that the extrinsic factor is crucial for tailoring the XOR-SAT problem to LDPC decoding. Can you explain why it's so vital for achieving this high performance and accuracy? And if it's so important, what happens if it's left out? Does it just fail?
Right. The extrinsic factor, mathematically represented by that term NJ-R1 RJG-GQJ in the HLDPC function. It's precisely what captures the correlation between the decoded bits and the channel information. Essentially, it measures how much the current decoded bit aligns with the noisy signal we originally received from the communication channel. Without it, the decoder would just be trying to satisfy the parity checks, which, as we said, could lead to any valid code word that fits the code's rules. Its importance lies in breaking the symmetry between code words. Think about it. An LDPC code might have multiple valid code words. The problem is only one of them was the original message, and only one is the closest to the noisy signal you received. Without the extrinsic factor, the solver might converge to any valid code word that satisfies the parity checks, regardless of how far it is from the receipt signal. It would be like a compass that points you to a treasure chest, but not necessarily the right one that's buried nearest to your current position. The extrinsic factor biases the solution toward the one that is closest to the actual received signal, guiding you to the most probable original message. It provides that essential context, and the experiments shown in Fig B4, they clearly demonstrate this critical role. Without the extrinsic factor, as seen in Fig 4a and 4e, many decoding cases fail to converge. They just never find a valid code word at all. Worse, they can lead to valid mismatch errors where the decoder does find a valid code word, but it's not the one that was transmitted.
Oh, that sounds particularly bad.
It is. It's particularly insidious because the decoder thinks it succeeded, but the data is wrong. Or it can even lead to completely invalid results, where constraints aren't satisfied. However, with the extrinsic factor incorporated, as shown in Figure 4b and Ford, the percentage of match-correct decoding is significantly higher, and errors are dramatically reduced. This factor ensures fewer valid mismatches, which are often much harder to recover from than completely invalid words because the system might not even detect the error.
That makes perfect sense. You need that channel information, that compass, to guide you to the specific valid code word that was most likely sent. Otherwise, you're just solving a puzzle without the full context. Now, the paper also discusses the flipping scheme, whether to flip just one bit or multiple bits during each iteration of the decoding process. It seems intuitive that flipping multiple bits would be faster, but does that introduce any risk? Could a large simultaneous flip actually make the decoder overshoot the correct solution or push it into a local minimum it can't escape from?
That's a very perceptive question, yeah. And it's a common concern with gradient-based optimization. In theory, large steps could indeed lead to overshooting or getting stuck. However, the findings here, which align with a lot of prior research in this area, strongly indicate that multi-bit flipping strategies consistently lead to much faster convergence and better performance for this type of problem. When multiple bits that satisfy a certain threshold condition are identified and flipped simultaneously in a single iteration, the algorithm makes larger, more efficient hops across the optimization landscape. You can see this beautifully illustrated in Figure 5b. This allows it to quickly escape those shallow local minima and converge to a valid code word much more rapidly. The risk seems to be mitigated by the careful design of the objective function and the thresholding logic, which ensure these multiple flips are still guided towards overall improvement. In contrast, single-bit flips, shown in Figure 5a, lead to very tiny, slow changes in the number of satisfied constraints. The algorithm essentially creeps along the landscape, making painstaking progress. It's just slow. Figure 5c illustrates this dramatically in terms of performance. The single-bit flipping error rates are far, far worse than multi-bit flipping. Even when given significantly more iterations, they show 500 iterations for single-bit versus just 10 for multi-bit flipping. So the data overwhelmingly supports multi-bit flipping as the unequivocally favorable strategy for faster, more efficient, and ultimately more accurate decoding. You want to make big, decisive, but guided moves, not tiny, hesitant steps, especially when time is of the essence.
It's fascinating how making more decisive moves, when properly guided, actually leads to a better outcome here. Like any sophisticated algorithm, though, there are parameters you can adjust, often called hyperparameters, to fine-tune and optimize performance. The paper details the impact of these, specifically tau, theta, and eta. How do these settings influence the MPXRSA decoder, and what does that mean for someone implementing this in the real world? Do you need a PhD to tune it?
Well, maybe not a PhD, but you certainly need to pay attention. You're right, these hyperparameters are absolutely critical for achieving optimal decoding performance, and understanding their role is key to practical implementation and successful deployment. It's about finding that sweet spot for the algorithm to operate most effectively. Let's break them down. First, tau, the MP-constrained constant. This parameter is directly associated with the margin propagation function itself. If tau is chosen to be too small, the MP equation behaves like a winner-take-all formulation. In this scenario, only one variable's gradient becomes dominant, effectively overriding the influence of other variables. This is detrimental to overall decoding performance because it limits the search space too much, preventing the algorithm from fully exploring potential solutions. The authors found through their extensive experiments that setting to a sufficiently large value, specifically equal to m, the total number of clauses or parity checks, yielded the best results. This value ensures a more balanced contribution from all variables in the gradient calculation, allowing for a more nuanced and effective search. You can see the clear impact in Figure 6a and 6pen error rates are significantly lower when a PO is appropriately set, specifically when it's close to m. Next is F, theta, the decision threshold. This threshold is what determines when a bit should be flipped. The experiments in Figure 6b and 6e clearly show that a flipping threshold, very close to 0 but crucially not positive, produces better bit error rate, BER, and frame error rate, SER. If theta is set to a value greater than 0, the results are described as catastrophic.
Catastrophic. Wow.
Yeah, catastrophic, meaning the decoder fails almost completely, performance just plummets. It's almost like walking a tightrope too far one way, and your data goes completely off the rails. This suggests a very narrow optimal range for this parameter, underscoring its immense importance. It almost makes you wonder what inspired them to explore values that close to 0 in the first place, leading to such a sensitive but critical tuning point. It's quite delicate. And finally, the learning rate. This parameter controls the step size of the gradient update during each iteration. As with any gradient-based optimization algorithm, selecting the right learning rate is a delicate balance. If E is too large, the algorithm can overshoot the optimum solution, leading to oscillations or even divergence, making it unstable. If it's too small, it will take an excessively large number of iterations to converge, making the process inefficient and slow. Figure 6e and 6f indicate that a learning rate between 0.01 and 0.001 provides the best balance for both BER and FRAR, achieving fast convergence without overshooting or getting bogged down. So for anyone implementing this, careful data-driven tuning of these parameters is absolutely essential for squeezing out the best possible performance and efficiency. It takes some experimentation.
It's fascinating how crucial these seemingly small numerical values can be for an algorithm's overall behavior. A tiny change in theta, and boom, catastrophic failure. So with all these innovations, the new objective function, margin propagation, the multi-bit flipping, and careful hyperparameter tuning, how does the MPXOR-S8 algorithm actually stack up against the best decoders out there? Like a sum product algorithm, SPA, which is considered the gold standard for performance. Where does it really shine in real-world benchmarks?
This is where the proposed algorithm truly shines and makes its compelling case as a significant breakthrough. The performance metrics are genuinely impressive across the board. First, on error rates, bit error rate or BER, and frame error rate or FR. For various standard codes, including powerful Boschuttery-Hockenham, BCH codes, fundamental Hamming codes, and widely used codes like EGLDPC, PEG, and the demanding IE 802.3 codes used in 10 gigabit Ethernet, the MP-XOR-SAT algorithm consistently achieves BER that are within an astounding 0.1 dB of the sum product algorithm, SPA. You can see this vividly in Figures 7 and 9 of the paper. This is a remarkable feat, as SPA is the benchmark for its near-optimal performance.
And 0.1 dB is tiny, right? Almost negligible in practice.
Exactly. It represents an extremely small difference in error probability. For many practical communication systems, this difference is almost negligible, meaning MP-XOR-SAT delivers virtually identical data reliability. Furthermore, it significantly outperforms other gradient descent bit flipping algorithms, which often required 300 to 1,000 iterations to even approach BP performance. The MP-XOR-SAT algorithm achieves this in just 30 to 100 iterations. That's an order of magnitude faster convergence for comparable performance. It gets there much, much quicker. Second, let's consider computational complexity. In terms of algorithmic complexity per iteration, using the standard O notation, the MP-XOR-S algorithm boasts the complexity of O m log m. Now, to put that in perspective, L log m scales much, much more gently as the code size m grows, compared to SPA, which is O2m plus O2n, where O and OGA are much larger factors related to the code structure.
So it scales better for bigger, more complex codes.
Precisely. Imagine the difference between searching a phone book efficiently using a structured lookup, that's kind of like Mengelog, versus having to check every single entry multiple times over. More like the complex SPA. This isn't just a small optimization, it's a fundamental shift in how the workload scales, making it viable for truly massive data streams. Table 3 in the paper clearly details this lower complexity compared to SPA, self-corrected minsum, SCMS, and neural offset minsum, NOMS algorithms. This simplified computational profile translates directly into faster processing times and less energy consumed per operation. Third, and this is perhaps the most compelling advantage for practical applications, is hardware complexity. The core design, by modeling on logarithmic values and cleverly using margin propagation, fundamentally eliminates the use of complex computations like multiplication and division. As we've discussed, these operations are a significant overhead in hardware, demanding more transistors, more power, and more time. Instead, the MP-XOR-SAT relies predominantly on much simpler operations: additions, subtractions, and comparisons. Table 4 highlights this drastic reduction in the required number of multipliers and comparators compared to other GDBF algorithms in SPA. The MP function itself, for example, can be implemented with a remarkably simple 2-transistor block for a single input in analog circuits, making it incredibly efficient for analog or mixed signal implementations. This translates directly into smaller chip area, lower manufacturing costs, and significantly reduced power consumption. Finally, the paper also addresses robustness to quantization. This is absolutely crucial for real-world hardware implementations. Digital circuits typically use fixed-point arithmetic, meaning they approximate floating-point numbers with a limited number of bits. This conversion process, called quantization, can often degrade performance for many algorithms. Importantly, the paper shows that this performance superiority of MP-XOR-SAT holds despite the quantization of inputs, as illustrated in Figure 8. This means the algorithm is robust enough for practical, real-world hardware implementations, where fixed-point arithmetic is a common necessity and a frequent challenge for maintaining performance. It still works well even when you simplify the numbers.
Wow. Okay, let me try to wrap my head around that again. We're talking about a decoder that delivers almost identical performance to the current best-in-class, the sum product algorithm, which itself is known for near-optimal error correction. Yet, it requires an incredible 10 times fewer iterations than other similar algorithms. And it's fundamentally simpler and cheaper to build in hardware because it completely sidesteps complex multiplication operations. That's a truly remarkable leap in efficiency. It means less power, less heat, smaller chip size, and faster decoding, all without compromising on data integrity. It fundamentally redefines the trade-offs we've always had to accept in digital communication. It's huge.
It really is. The MP-XOR-S solver truly stands out not just for its performance metrics, but because its objective function is fundamentally different from the generalized forms of other gradient descent bit-flipping algorithms that have been explored for decades. This difference in the foundational mathematical approach is precisely what allows it to converge faster and achieve superior performance with significantly reduced complexity. It's not just an optimized version of an old idea, it's a fresh, purpose-built perspective that addresses the computational challenges head-on. This makes it a prime example of a hardware-aware solution. By designing the algorithm specifically to avoid computationally expensive operations like multiplication, the authors have paved the way for more efficient, lower power, and smaller hardware implementations. This is absolutely crucial across a vast range of applications. For tiny battery-constrained IoT devices where every milliwatt counts, this means longer battery life and smaller form factors for smarter, ubiquitous sensors. For power-constrained deep space probes operating on very limited energy budgets tens of millions of miles away, this means more reliable data transmission for longer missions, pushing the boundaries of scientific exploration. And for next-generation high-speed communication systems like advanced Wi-Fi or 6G, this translates to lower latency and higher throughput, enabling truly instantaneous data exchange. It's about thinking about the silicon from the very beginning of the algorithm design process.
So it's not just a theoretical improvement. It's a practical blueprint for the next generation of digital communication systems. It's opening doors for devices and applications that might have been impossible or simply too expensive or power-hungry to build before. It truly empowers innovation at the hardware level. The paper even goes a step further, mentioning that future work will focus on practical implementations in the analog domain. What kind of impact could that have? Taking this already incredibly efficient digital algorithm and translating it into the analog realm sounds like it could unlock even more radical benefits. Is that right?
Moving this algorithm into the analog or mixed signal domain could indeed yield tremendous advantages in power and area, pushing the boundaries even further. Yes. Analog circuits, especially for functions like margin propagation, can be incredibly compact and energy efficient because they perform computations by directly manipulating voltages or currents, rather than discrete zeros in one chill. This can be inherently faster and consume far less power for certain operations. For instance, in an analog implementation, you could potentially eliminate the need for any circuit to implement the additions entirely, as sums might be achieved simply by combining currents or voltages. That further reduces complexity, power draw, and latency. Imagine microchips that consume even less power and take up even less space than their digital counterparts, performing complex error correction at very high speeds. This would be perfect for extremely demanding applications where every joule of energy and every millimeter of space counts. Think implantable medical devices that need to be tiny and last for years on a single charge. Or ultra long-range sensor networks in remote environments, or those deep space missions we talked about requiring unprecedented energy efficiency for distant communications. This truly pushes the boundaries of efficient communication technology, moving us towards computing that's more integrated, more organic, and far less resource intensive. It opens up some really exciting possibilities. Hashtag tag outro.
So what does this deep dive into margin propagation-based XOR ASAT solvers teach us? It's a brilliant example of how innovative algorithmic design can fundamentally overcome long-standing engineering trade-offs, giving us high performance without the usual high cost in terms of power, area, or computational complexity. We've seen how by reframing a problem, treating LDPC decoding as a specialized XOR ISET problem, and then introducing clever hardware-aware approximations like margin propagation, we can create solutions that are not only powerful, but also incredibly practical for the real world.
It profoundly highlights that there's always more to learn, and by questioning existing assumptions like the necessity of complex multiplications and decoding architectures, we can unlock truly revolutionary advancements. The blend of abstract mathematics and practical hardware considerations, from the very first step of designing an objective function to its final power-efficient implementation, is a testament to ingenious interdisciplinary problem solving. This kind of thinking is what drives true innovation forward, I believe.
So, what does this all mean for you, the listener, and the future you're building? Think about how much of our digital lives already depend on reliable data. Every photo you share, every financial transaction, every signal from a distant probe relies on this invisible layer of error correction. Now imagine that layer becoming dramatically more efficient. What if the next generation of your smart devices, autonomous vehicles, or even those incredible space probes exploring distant planets are running on these incredibly efficient multiplier-less algorithms? It's silently ensuring your data arrives perfectly, using barely any power, enabling entirely new possibilities we can only begin to imagine. Longer battery life for wearables, smaller, more powerful embedded systems for medical tech, or even completely new forms of communication in challenging environments. It's a powerful reminder of the invisible innovations that shape our future, making the seemingly impossible possible. We hope you enjoyed this deep dive into the fascinating world of ultra-efficient error correction. Join us next time as we unpack another groundbreaking topic.